Hi everybody, hope you're doing well. In the present lecture, we will discuss the preliminaries of second quantization or field quantization. Okay, the recommended textbook will be Field Quantization by Greiner and Reinhardt. This guy, Greiner, has a series on quantum mechanics books. They are very didactical and pedagogical for many purposes. But you also can find out in many other references the subject on second quantization. And just to remember, first quantization is the quantization of classical particles. The description of a classical particle in the quantum realm, in the quantum world, was called the first quantization. Okay, it was done first, and for a classical particle, you have a canonical variables, a set of canonical variables. Usually, I'm using just one dimension for space here: position x of t and momentum p of t. They are canonical in the sense that a Poisson bracket is equal to 1. Remember that the Poisson bracket of two variables depending on position and momentum are just the derivative of the first with respect to position, the derivative of the second with respect to the momentum, and reverse the order, okay? So derivative of b with respect position, derivative of a with respect momentum, okay? So for two variables, a Poisson bracket means you need to do that calculation here. And in quantum mechanics, you replace by a procedure which was described first by Dirac. You must replace Poisson bracket by a commutator. Okay, so this is just commutator of operators, which are usually represented by matrices, and in quantum mechanics, observables are Hermitian operators. Okay, so you need to replace a Poisson bracket by commutators. These operators the operators act on a Hilbert space, and the Hilbert space, in Hilbert space, the physical state is represented by some function psi, which can be just projected out into the basis of position, and you'll find out a field depending on position and time. Okay, this field must satisfy some equation, the Schrödinger equation, and the probability of finding a particle is proportional, is equal. As a matter of fact, this is a probability density. It is equal to the modulus squared of that field. So a classical particle in a classical world, the canonical variables are replaced by operators acting on some Hilbert space, and the cat state can be projected out into the position basis, which will lead to the so-called wave function, which is a field. And therefore, classical particles will be described by a classical field in quantum mechanics when we are dealing with the first quantization scheme here. But notice that in classical physics, in classical mechanics, we have also fields. The electromagnetic field, which is already a field in classical mechanics, classical physics, and we need to quantize it. So what is the quantum of the electromagnetic field? We know that the quanta are called photons. So a second quantization historically was given that name, a second quantization, because First, a theory for a classical particle was quantized. Rules for classical particles in quantum mechanics. The classical physics was translated into quantum mechanics, and classical particles in quantum mechanics are described by a classical field, which is this object, which is a wave function. Okay, but what for the classical fields, the electromagnetic field, or perhaps if I want to transform this field into an operator in quantum mechanics, what can we do to quantize a field? All right. Remember that for particles, the position and momentum only depend on time, and the field has position and time, or momentum and time, as if you represent it in another basis, in the basis of momentum, perhaps they are functions of the degrees of freedom are functions of, in this case, position and time. So they are parameterized by position and time. So what can we do to quantize a field? That's the subject which concerns second quantization, or field quantization. And to do that, we will use first, we will describe first the algebra of some very interesting operators, which is called the number representation, and creation and annihilation operators. Okay, and there are two possibilities: Bosonic and Fermionic algebras. So here we'll find out two possibilities, which are bosons or fermions. In this case, remember that a boson has a spin of an integer value, and the fermion would correspond to half integer values for spin. Okay, 1/2, 3/2, and all that. So there are two possibilities for quantizing a field. Okay, we are not dealing in two space dimensions, which has some particularities, but even there, for the most majority of the systems, you can make a field quantization, and which will lead to the description as a bosonic field or a fermionic field. Okay, so the rules of quantization can assume one of these two algebras. For integer spin particles, bosonic field, and for half spin particles, a fermionic field will be used in the description. So what is number representation? Okay, number representation assumes that you have a number operator. So suppose there is an n sub alpha here. The alpha corresponds to a set of quantum numbers. So this is the physical state, the quantum state. It is a label which say what quantum state we are dealing with. Usually you can use momentum and the spin value in the z direction. Okay, so there are, in 3 dimensions of space, 4 components describing this alpha here. You also could use another parameter just to distinguish between distinguishable particles. You could have bosons, which are photons, and in the same system you could have phonons. Okay, in a material you could have phonons, photons, magnons. So perhaps you could label this into this, but usually you could use another letter in the Latin alphabet or in some Greek alphabet. Okay, but this is corresponding to a set of quantum numbers. So a quantum state, also a quantum state would be atomic orbitals. So this is momentum or plane waves as basis functions, so plane waves. It could be atomic orbitals, so n, l, m, and the spin for a particle. I'm not saying that this is up or down because a particle could have a boson and could have some higher spin, or a fermion with higher spin than electrons. So the alpha here corresponds to a set of parameters specifying the quantum state of that particle. Okay, and this is called the number operator. Okay, number operator. A number operator acts on something called Fock space, acts on a so-called Fock space, right? Which is just some kind of a Hilbert space where the vectors, or where the ket vectors, represent the number of particles in that state. All right. So in Fock space, you have a number operator acting on some ket, okay, on some ket, and the result is the number of particles in that state times the ket representing that state. I am using here the usual convention of Sakurai, for instance, where the eigenvalue and the eigenvector are labeled the same way. So just to give an example, suppose you have a boson system and you have a state in some wave vector, okay? Remember, momentum and wave vector are just related by h bar k, so you could find also a representation with wave vectors. So suppose some wave vector k and the spin projection plus 1, okay, for a boson of spin 1. So suppose this is the number operator and it acts on a state with, suppose, 10 particles in that k with projection of helicity of or spin plus 1. Okay, you have 10 photons to be definite. For the sake of simplicity, consider, suppose, photons. Okay, so your number operator acting on that vector state will produce the number of particles, and of course the eigenvector repeats. Okay, so this is an eigenvalue equation, and Fock space refers to the space where the number of particles of a given type is precisely defined. Okay, so this is the Fock space. Okay, and numbers. Any number operator can have only integers as eigenvalues. Okay, so the number operator has integers. Okay, starting from 0. So no particles, 1 particle, 2 particles, and we will specify for bosons and for fermions there are distinctions which we'll discuss right now. So there is a number operator which only can produce integer eigenvalues, and there is something called a creation operator for a given set of quantum numbers. So it creates a particle at state alpha. So this is a creation operator. Okay, and there is also a annihilation operator. Annihilation operator. And when they act on something, suppose A alpha acting on some state alpha, it will be proportional to the state n alpha minus 1. Okay, so it annihilates a particle in the state n alpha. Suppose you have 10 photons, to be specific, in a bosonic system, and you apply annihilation operator. It annihilates a photon in the state alpha, and you arrive at the final state with n minus 1 photons. And also you can have a creation operator, which when acting on some ket with n particles in that quantum state will produce n particles plus 1. Okay, so proportional. The proportionality factors we will discuss when dealing with the specific cases of bosonic and fermionic fields. So we need to know number operators, annihilation and creation operators, and the number operator, whatever, for bosons or for fermions, is always defined as the product of the annihilation, the creation operator and the annihilation operator in this order. Okay, so number operator is defined this way here. Okay, it's just the product of a dagger and a in the state alpha. A dagger is just the transpose conjugated of a, but a of alpha, which is annihilation operator, is not Hermitian, because the dagger is distinct from their operator. So the dagger, the transpose conjugated of the creation, the annihilation, is the creation operator, and vice versa. They are not Hermitian. But the number operator, it is Hermitian, or self-adjoint, if you prefer. Okay, this operator is Hermitian, but annihilation or creation operators are not. Right? So let's proceed. Just defining now a boson algebra. Okay, so boson algebra. It is used to describe bosonic particles, and in the second quantized version, bosonic fields. Okay, so boson algebras or boson algebra. Okay, remember, it's worth of remembering spins for bosons are integers. Okay, and for bosons, a state is a symmetric object. Under permutation. So if you switch the states of two particles, a plus sign will emerge. Switching the states of two bosons will produce nothing but a plus sign. Okay, and bosons do not need to satisfy the Pauli exclusion principle. So you can put any number of bosons in a given state. So for a given state, n alpha, the eigenvalues of this, I'm writing as a set of eigenvalues, could be 0, 1, 2, 3, for any integer going to infinity. Okay, so any integer. So the eigenvalues, so n alpha is in the integer numbers, the positive integers including 0. Okay, so this is what a number of bosons in a given state alpha can be. You could put 0 bosons in a state, so it is a vacuum, or 1, or 2, or 3, or 4, or 5, any integer, a positive integer. Negative integers, or you could not do that because it's nonsensical. It does not make any sense to put a negative number of particles. The number of particles, which is described by a Fock space, must be an integer. Okay, so you could define a vacuum, okay, a zero of particles, a vacuum, a general vacuum which has no particles at all, and you could define so this vacuum as this state here, 1, 0, 0, 0. It goes forever because for bosons you can put an infinite number of bosons in a given state. So the vacuum of the alpha state corresponds to 0, okay? Corresponds to no particles in the state alpha. So you could write a state with one boson at the quantum state alpha, which would be this vector, a two particle state, which could be represented by some vector like this, okay, and so on. All right. So this is what a Fock space would mean. Okay. Well, so annihilation operator acting on the annihilation operator acting on the vacuum of that state, it is 0. It is the null vector. Okay, it is this vector here because there are no particles in this state. So you cannot annihilate from nothing, from the vacuum. You cannot annihilate a particle where there is none. There are no particles in vacuum, so you cannot annihilate that state. It produces a 0, a null vector. Okay, but you could create a particle in the vacuum. It will produce the state 1, and this would be done by acting with the creation operator. You could apply it again to the state with one particle. For boson, it works just fine. You can put two particles, but notice that this is the application of the operator twice to the vacuum. Okay, and you can apply again to the state of 1, to the state of 2, sorry, state of 2 particles, and you will produce, borrowing some ideas from a previous lecture on the harmonic oscillator from ladder operators. Remember, for the harmonic oscillator, you can have a ladder operator which creates one quantum, two quantums, three quanta, and so on and so forth, of the unit of energy of the quantum harmonic oscillator. Okay, so the idea for bosons is just to represent bosons by ladder operators in as much the same way you do it for quantum levels of a harmonic oscillator. So a normalization corresponds to picking up this number here, this 2 here, and you produce a state minus plus 1, sorry, here it will be 3 here, and when you act this, it will produce a square root of 2 here. This produces a square root of 1, square root of 3, the state with 3 particles, and you can go on just producing something like this. The action of a creation operator on a state with n particles at that quantum state, the set of quantum numbers alpha, will produce a square root of n plus 1, and the state is raised by 1 particle. You just inserted 1 more particle to that state. Also, for the vacuum, you could not eliminate anything because there are no particles there. But if you try to annihilate a particle in the state with n particles, it produces a proportionality factor which goes with the square root of n alpha and produces a state with 1 particle less. So n alpha minus 1. Okay, you just lower the number of particles applying annihilation operator. Okay, this is what is meant by applying the annihilation operator to a ket state representing n particles and bosons, right? And of course, if you apply number operator to n alpha, it is just you can apply this and then apply that. You can just show that this is just the eigenvalue times the eigenvector. Okay, remember, n alpha is just a dagger of alpha a, okay, in that order. It is Hermitian, and the eigenvalues are just positive integers starting from 0 because you can have the vacuum, right? The most general vacuum is a vacuum. So this is the definition of vacuum for particles in the alpha state. But the general vacuum is a vacuum which you don't need to specify what state because there are zeros in any state. So in the alpha 1 state, in the alpha 2 state, in the alpha 3 state, in any given set of quantum numbers, there are no particles. So no particles at all in the general vacuum. So if you apply any annihilation operator to the vacuum, you get 0, the null vector, right? Well, of course, you can construct for many quantum states allowed in your system, you can construct a general state with n alpha particles in the state alpha, say alpha 1, n alpha 2 particles, n alpha 3 particles. You can construct a state with any number of particles, any number of bosons, which is just the state n alpha 1 times the state n alpha 2 times the state n alpha 3 in general, okay? If you're not considering entanglement and all that, you could factorize the state in that manner. And this way, to obtain for any, suppose any given alpha, to obtain this state, you just need to pick up the vacuum. So just to write this general state here. So write general states n alpha 1, n alpha 2, n alpha 3, okay? Or I could use another letters here, perhaps alpha, beta, gamma, and you just need to pick up the vacuum, the general vacuum, and apply n alpha 1 times the creation operator to the vacuum, and you will create n alpha 1 particles in that state. But the normalization factor here is the square root of n alpha 1 factorial. N alpha 1 factorial. And for the second state here, you need to apply the A alpha 2, N alpha 2 times to the vacuum divided by the square root of N alpha 2 factorial. All right, and you can apply, you can construct a state, a general state having n alpha 1 particles in the state alpha 1, n alpha 2 particles in the state alpha 2, n alpha 3 particles in the state alpha 3, and so on and so forth for bosons. And these numbers can be anything between 0 and infinite, but they must be integers. Okay, and you could just switch the positions here for the operators because they are bosons. It doesn't matter if you create this particle first, this set of particles first, or that set of particles. It doesn't matter. For bosons, you can do it in any order, okay? The order is not relevant for bosons, right? So let us just write the algebra for bosons. The algebra for bosons is the following. You need to use commutators. Remember, commutators of two matrices are just that operation. And anti-commutators, we define by curly brackets, is just replacing the minus by a plus sign, okay? A relevant aspect, very relevant aspect when working with this algebras for bosons and for fermions. For bosons, we will choose the commutators, is that operations like this, A, B, C, the commutator of A with the product BC can be written either way as a commutator between A and B times C plus B times the commutator with of A and C, or you can replace the commutators by anti-commutators. And the relation holds for both you if you choose commutators or anti-commutators, but you need to change sign here. Okay, so this is a very important relation when using. So this is a comma here. This is an anti-commutator of A and C. Okay, I hope you can see it well. I don't know if it's clear in the board, but this relation here, you can write it as a sum of two commutators in this way here, or two anti-commutators in this way here, right? And for bosons, we always choose something related to commutators. Okay, so let me write down the algebra. Suppose you have a quantum state alpha and a quantum state beta, the commutator of the annihilation operator is 0. Also for the creation operators, okay, commutator of two creation operators for bosons is 0, okay, and the commutator of a given annihilation operator in the quantum state alpha with the creation operator in the quantum state beta is just the Kronecker delta. Okay, so this is the set of relations you need to establish the algebra. For bosons, this establish the bosonic algebra. Okay, so this delta is 1 if the quantum state alpha is equal to the quantum state beta, or 0 if the quantum state, the set of quantum numbers labeling the state alpha, is distinct from the quantum numbers labeling the state beta. Okay, so this is the algebra for bosons. What does that mean, really? Well, here it states that you can annihilate the state alpha and then annihilate the state beta, or you can annihilate state beta and then annihilate the state alpha, and it doesn't matter what order. Okay, for bosons the order is not important. So picking up this relation here, if you try to create a particle in the state beta, or you try to create a particle in the state alpha first, depending on the order you are choosing, okay, it doesn't matter, because the commutator of a alpha dagger with a beta dagger is 0. So it implies that if you try to create a particle in the state beta first and then create a particle in the alpha state, it is the same as, if you move this factor to the right hand side here, it is the same as tries to create the particle in the state alpha first and then create a particle in the state beta. It doesn't matter the order, okay? So if you apply this to a vacuum, a state where you create first the state, a particle in the state beta and then the particle in the state alpha, it is no different than creating first alpha and then beta. Or in another way to think about, you can permutate, switch the labels of the particles, and that produces a plus sign. Okay, this is a plus sign. You are switching the labels. Alpha beta in this order, beta alpha in the reversed order. You are switching two operators. You are switching or permutating two labels, and for bosons you have a plus sign. So this is compatible with the spin statistics theorem. For satisfying the spin statistics theorem for bosons, it implies that creating a boson in the state alpha and creating a boson in the state beta, it doesn't matter the order. You can do it any order. It's just implied by this algebra. Okay, so this automatically satisfy the bosonic relations required by the spin statistics theorem. Okay. Well, so far so good, I guess. But there are possible representations of the operators as matrices. Okay, acting on the Fock space. So suppose the Fock space for the state alpha corresponds to this vector. A state with one boson in the state alpha correspond to this vector. The second one, a state with two bosons, it is a number representation. That's why it's called number representation, because the states are labeled by the number of particles in each set of quantum labels you need to use for specifying a quantum state. Usually, as I said previously, momentum and spin of the particle, but it could be atomic orbitals or whatever. Okay, so you can go on forever, because for bosons you can have 1, 0, 1, 2, 3, 4, go to infinity. So these vectors, as a matter of fact, are infinite dimensional, and a number operator, a representation of the number operator acting on this space corresponding to the numbers in the state alpha is 0. The eigenvalues I can put in the diagonal: 0, 1, 2, 3, 4, 5, and zeros outside the diagonal. So the diagonal corresponds to integer numbers, which are exactly the possible eigenvalues for the occupation number in a given state alpha. And the operator A can be written this way here: zeros in the diagonal, zeros in the lower the lower positions of the matrix, and just above the main diagonal you have square root of 1, square root of 2, square root of 3, square root of 4, square root of 5, the square roots of the integers, starting from 1, 1, 2, 3, 4, and it goes on forever. So notice that when this thing here acts on the state of one particle, it produces the vacuum state. All right, you annihilate a particle here. If you act on the state 2 here, you'll have, because you have zeros here, okay, outside this above the main diagonal here, you have zeros otherwise. If you apply this to the state with 2 particles, you'll produce the state with 1 particle with proportionality factor the square root of 2. And of course, if you want to calculate what is the creation operator, it's just to take the transposed conjugate of this matrix. You'll find out something like zeros in the main diagonal, and the square roots will appear here. Square root of 2, square root of 3, and all that. Okay, so you can do it properly, but the dimensionality of this matrix is an n by n, with this n going to infinity. So square root of 1, 2, 3, square root of 4, square root of 5, you go forever. Okay, so far so good. I'll just ask you to do some exercises here. They are very interesting. So exercises. It can be a main exercise. Calculate the following commutators. Okay, calculate that. A of alpha with the number operator in the state beta. Alpha can be equal or distinct from beta. Of course, as a hint, for alpha distinct from beta, it will produce 0, okay? But for alpha equals to beta, you need to be careful. So calculate this first, and calculate this in the second. So I want you to calculate this and that. All right, so remember that n beta is just the number operator in the state beta. But you can choose alpha equal to beta or distinct from. And I am just saying that you can show it quite easily that for alpha equal to beta, you need to calculate something, because here you have something like that A, B, C, and you need to work out the things. But if alpha is distinct from beta, it will produce zero here and here, okay? But this is the first part. The second part of the exercise is consider the Hamiltonian for a free bosonic system. For free bosons, okay? So non-interacting bosons. The Hamiltonian is this one. You have bosons in allowed quantum states alpha. This alpha can go from 1 to infinity, from some set of discrete values. It could also be a continuum, but suppose there is a set of quantum states here in a discrete manner, and you have the Hamiltonian is equal to the energy of a single particle in the state alpha times the number operator in that state alpha. Okay, the number operator. So this Hamiltonian is a matrix. Okay, it is a matrix. It is an operator. It is Hermitian. And of course, if you want to calculate for a given state, suppose you have a given state with n alpha particles only. With a given state alpha, you have only particles in that state alpha. I'll say beta just to use a distinct symbol here to represent the state. Suppose the state of the system is you only have bosons in the state beta. What is the average energy of your system? You can calculate this thing here. And of course, you will obtain the energy in the beta state, okay, times the number of particles in that state. Okay. So suppose a photon, a given photon with a given momentum and spin has energy of 1 electron volt. One photon has 1 electron volt of energy, right? If you have 10 photons, what is the energy? Of course, the total energy will be the energy of a single photon times the number of photons in that state. So you'll have in my example here 10 electron volts because you have 10 photons with 1 electron volt each, right? So this is a very intuitive Hamiltonian. The Hamiltonian of the system consists of writing the total energy of the system as a non-interacting system, because when you have interactions, things change here. But with non-interacting system, what do you have? You have the energy of a single particle times the number of particles in the system. Okay, this is pretty obvious. Okay, and this Hamiltonian has as eigenstates number of particles. Okay, so this is diagonalized by the number representation. Okay, so a total energy in a state with n particles in the state alpha 1, n particles, another number in the state alpha 2, and goes on, will be the sum of E alpha and alpha, the alphas here. So suppose you have particles in the state alpha 1, so you'll have E alpha 1 times the number of particles in that state, plus E alpha 2, the number of particles in the state alpha 2, and so on, times times the eigenvector, okay? Because this is an eigenvalue equation, eigenvalue, eigenvector, okay, alpha 2 and so on. All right, so this is it. Well, I'm just introducing this Hamiltonian, but what I want you to do, okay, consider this Hamiltonian, determine the equations of motion of course. The A dagger and A are operators, so you need to use, of course, a Heisenberg picture here, the equations of motions in the Heisenberg picture for A dagger of alpha, A of alpha, okay, and solve them. Find the time evolution or solve them, okay, solve these equations. So what you need to do, for instance, for the A alpha, you need to calculate this equation. I, H bar, the time derivative of that operator is just the commutator of that operator with the Hamiltonian, because this is the Heisenberg equation of motion for that operator. Also for H dagger, the A dagger, sorry, and if you take a look at the form of these equations, if you calculate this, you also will, if you pay attention to what is this operator, you don't need to calculate a second commutator here, because you just need to take the transpose conjugate of the equation for the A alpha and you find out the equation for the A dagger, okay? Also try to find out here the N alpha, okay? So A dagger alpha, A alpha, and the number operator. You'll find out that the number operator commutes with the Hamiltonian, so you'll find out that the number of particles is conserved, because anything which commutes with the Hamiltonian doesn't change in time, and therefore it is conserved, it's a conserved quantity. So this Hamiltonian here corresponds to a system with a given number of particles, and that for the eigenstates of this Hamiltonian, the eigenstates are states with a given number, a definite number of particles, and this number of particles is unchanged. The number of particles is conserved, okay? If you put interactions into your system, the number of particles may not conserve anymore, okay? But we will see that later. But now I need you to do that. Consider the Hamiltonian of a free bosonic system and calculate that, all right? Well, for bosons, that's it. For fermions, we can do the same steps. So fermions or fermion algebra. So fermion algebra here. Fermion algebra. Remember, fermions are half integer spins, and they are anti-symmetric under permutation. They must obey Pauli principle. Pauli's exclusion principle, and therefore you can only have for the set in a given state alpha, for the set of numbers here, allowed for the occupation 0 or 1 in the state alpha. Okay, there are only two possibilities for fermions. The state may be occupied by one fermion or none. You cannot have two fermions in a given set of quantum numbers in a quantum state labeled by this alpha. You have only 0 or 1. These are the two possible eigenvalues for the operator n alpha. So for a given alpha, the operator is this one. The representation as a matrix is this one. There are two possible eigenvalues, 0 or 1. No fermion in that state, one fermion in that state. So the n alpha, when it acts on a given state, it produces the number times n alpha. And therefore, for a given alpha, for a given state alpha, you have two possible states. The state 1, 0, which corresponds to no particle, and the state 0, 1, which corresponds to one particle in that state. Okay. Notice that for bosons, you have an infinite dimensional vector here representing the vacuum, representing the one particle state, and so on. But for fermion, given the state alpha, in that state you can only have 0 or 1. So this, for the representation in a given alpha set of parameters of quantum labels, the matrix is a 2 by 2 matrix. Okay, so for spin half or half integers, the Fermion algebra could be represented in some way. It is possible to represent the matrices acting as a combinations of Pauli matrices. All right, but this is the representation of the number operator. Okay, so what can we do to obtain the most important property of fermions, which is the exclusion principle? You could only put one fermion in a given state or no fermion in that state. And I guess was Pascual Jordan which ingeniously find out a solution, very simple solution, just replacing commutators, which describe the boson algebra, by anti-commutators. I will use for the operators the number operator, the creation and annihilation operators, a distinct letter. Okay, I used A for bosons. I will use C for fermions. So C alpha anti-commutated with the C beta is 0. So you need to calculate this thing here, C alpha, C beta plus, instead of minus, which would correspond to bosons, you need to consider a plus sign. It's an anti-commutator. So anti-commuting algebra. If you want to find out a little bit more about these algebras and the relations to the Fermion algebra, you can just search for Grassmann. Okay, Grassmann was the mathematician which used, perhaps for the first time, and I'm not sure, but used the anti-commuting algebras, and they are linked to the fermion behavior. All right. So of course, for two fermions, the anti-commutator of the creation operators is also 0. So C alpha dagger C beta dagger plus C beta dagger, C alpha dagger, anti-commute. And finally, if you pick up some annihilation operator and you anti-commute with a creation operator, you'll find out the Kronecker delta. Okay, so they are almost the same, but boson commutators, fermion anti-commutators. This is what you need to do for finding out an algebra which ensures that your system will satisfy the Pauli exclusion principle. Why is that? Let us see a little bit more. So there is a vacuum, okay? Any operator acting on the vacuum produces the null vector, all right? So if you try to destroy one particle in a state which has none, it will produce the null vector. So this is null vector, as in the case of bosons. Okay, the annihilation operator can be defined by, in the vacuum, mainly the vacuum can be defined by this equation. There are no particles. If you try to annihilate one particle, it produces nothing because there are no particles there. Okay, so the C is the annihilation operator. The C beta, the C dagger of alpha of a given set of quantum numbers is the creation. Okay, and N is also defined the same way as for bosons. It is product of a creation times annihilation operator. It is the number operator. Same ideas apply. Annihilation operator is not Hermitian. The creation operator is a transposed conjugated of the creation operator of the annihilation operator. Sorry, so creation is transposed conjugated of the annihilation. And number is Hermitian because you can only have integer values for the occupation number. But for fermions, there are only two possibles, 0 or 1. The state is unoccupied or occupied. You cannot have anything else. You cannot put 2, 3, 4, any number of fermions in a given alpha state. You can only put one, just one or no fermions in that state. All right? But let us see what happens. Just remember these equations here. Suppose you pick up this equation here, C dagger alpha, C dagger beta, plus C dagger beta, C dagger alpha. It is 0 because it anti-commutes. And therefore, I can write this in the following way. C alpha, C beta, dagger. It could also be the same. It is the same equation for the annihilation operators here. But if I move this to the right hand side, I will have minus C beta, C alpha, the daggers, of course. And look what this produces a minus sign if you switch, if you permutate the particles, if you permutate the quantum states of the particles. Okay, you can create first the particle beta and then the particle in the state alpha. But if you do it in the reverse order, you switch the order, you'll get a minus sign. And that's what is needed for a fermionic algebra. Fermions must anti-commute, which means under parity, if you switch places of the particles, if you switch the order, you get a minus sign. All right? If you if you create first a particle alpha and then a particle beta, this corresponds to a minus sign with respect to creating first the beta particle and then the alpha particle. Okay, this corresponds to the anti-symmetrization needed for the quantum states of fermions. Right? So if you apply this to a vacuum, you will produce the state with one particle in alpha, suppose they are distinct, alpha and beta, and one particle in beta. But if you calculate in the reverse order, you create first the alpha particle and then the beta particle, you find out minus the alpha particle was created first. So I can keep moving the particles created first to the right. Okay, so I created this first and second this one, or this first and second that one. If you switch, if you permute the states, the label of the states, you will produce a minus sign. So this is compatible, it satisfies the Pauli exclusion principle. But let us see a little bit more about that. Okay, just look that. So this is for alpha distinct from beta here. Okay, but suppose you have alpha equal to beta, the same state. So this equation here produces the following: C alpha dagger, which is the square of the alpha dagger, is equal to minus the application of that operator squared, which means this operator is the null matrix. It needs to be the null matrix. Or you can look at directly here, alpha equals to beta, you get twice C alpha squared equals to 0, which means C alpha squared is C alpha dagger squared is equal to 0. What does that mean? Let us see. If I apply first a creation operator to a vacuum, I put one particle in the state alpha. Okay. Let me try to create another boson in the state alpha. So I already have one fermion, I already have one fermion in the state alpha, and I'm trying to create another fermion in that same state. So what we'll have C alpha dagger to the vacuum, because this is the state with one particle, and this is the square of the creation operator applied to a vacuum. But this square is the null matrix. So the null matrix applied to a vacuum produces the null vector. Okay, so 0. You cannot do that. If the state is filled with one particle and you try to put another one, 0. If you try to annihilate the vacuum, null vector. The result is the null vector. If you try to create a particle in the vacuum, okay, you create one particle in that state. You put one particle in that state. But if you try to put one more particle in that state, which is already filled with one particle, 0. You cannot do that. The result is 0. You'll have nothing, because you cannot create another particle in a state which is already filled with one particle. This fully satisfies the Pauli exclusion principle and the spin statistics theorem. For fermions, you can only put one particle or no particles in a given quantum state. So in the quantum state alpha, I can have only 0 or 1 particle. And the anti-commuting algebra of these operators automatically satisfy the requirement. Okay, you automatically satisfy the requirement. Of course, I can annihilate a particle. Okay, I can annihilate a particle in the state with one particle. I'll get the vacuum for that state. All right, so I can annihilate a particle if I have one particle. I can create a particle if I have no particle, but if I try to annihilate the vacuum, zero. If I try to put another particle, zero, right? Because they are fermions. And when related to what we see in the previous lecture, if you have a particle with momentum, suppose a state alpha, and another particle with a state beta, it can be, for instance, a P1, spin 1, a vector, momentum vector P2 and spin S2, they can collide and they produce, I'll call this the particle 1, this is particle 2. They can produce a particle 2 prime and a particle 1 primed, okay? But you cannot know what particle. So the final state is 1 prime and 2 primed, okay? This is the final state. Final state. But you cannot know if the particle 2 created 2 prime and 1 created 1 prime, or for fermions, what happened was this thing, the one particle colliding with the particle labeled by this label 2. This produced the 1 prime, and this produced the 2 prime. And these two graphs here, when they interact, these two graphs are interfering destructively. There is a minus sign. What represents this minus sign? This minus sign is corresponding to switching the labels of the particles. Okay, it corresponds to, in a given scenario, it corresponds to some switching of operators. Okay, and these are exactly done by the annihilation and creation operators for fermions satisfying an anti-commuting algebra. Okay, so this sign here is somewhat related to the switching of labels. Okay, I can just permutate the final states, and permutating final states corresponds to a minus sign. Okay. Well, I'll ask you to do the exercise, which is nearly the same as the previous. So the exercise: calculate the following commutators for fermion operators. Okay. Notice commutators. Okay. I want you to calculate C alpha commutated with the number beta. Okay. And I want you to calculate C alpha dagger with n beta, the number operators. Okay. Do that, please. And when you use this, you'll have something like A time commutated with some BC, and you need to use the anti-commutators, I guess AB, C minus B here, AC. You need to use anti-commutators. For bosons, you would use the commutator here, but for fermions, notice that, sorry, I switched the light interrupter, but I guess you can see now. And here you have a product. So n beta is a number operator. C dagger beta, C beta, they are A is this, B is this, and C is that. Okay, you need to use the algebra. All right, do the calculations. You work these things just nice and easy. I see no problem in doing that. Okay, so just calculate this thing, and then considering a system of free fermions whose Hamiltonian is given by same thing as previously, but now you have fermionic operators, C dagger alpha, C alpha, okay, fermionic operators here. What you need to do, consider this Hamiltonian, find out the equations of motion for C alpha dagger, the number operator, and solve for time evolution. So use Heisenberg equations of motion, calculate the equations of motion, determine the equations of motion, and solve the equations of motion. They are pretty easy to do. So suppose it's the same for the bosons, okay? Suppose there is a C alpha of t, and this is somewhat related to some initial value and something here, and some function of time here, which is just a function, okay? This is just a function. So the C0 times the function of time, you need to determine this function here, okay? This is what you need to do, okay? Well, there are representations for Fermion algebras. The operators could be, just to finish what I'm talking about here, you could use the Pauli matrices, but then for fermions in a given state, a C alpha matrix is just a matrix which acts on this space here, which is 1 0, and this state here which is 0 1. Okay, and the C alpha when acting on the state with one particle produces no particle, so it must multiply this row by this column, produce one here and zeros otherwise. Of course, the C dagger is just the transpose conjugated, and this is the representation of the C dagger. But notice that if you pick up the sigma x, sum up the Pauli matrix sigma y times the imaginary unit and divide it by 2, you'll find out exactly this. And this is the ladder operator for spin half. Okay, and of course, if you take the complex conjugate here, you'll find out the C alpha. So for each alpha, you would have an alpha here. But remember, I must emphasize this. This is just a representation, okay? It's not related directly to the spin of the particle, okay? It's just you could represent the operators as matrices, but because for fermions there are only two eigenvalues which are possible, for only two eigenvalues for only two eigenvalues, you can map this system using in a matrix representation using Pauli matrices. That's why you could represent these operators, the C and C dagger, using Pauli matrices. Of course, you could calculate the n alpha, which is 0, 0, 0, 1. So the eigenvalues is in the main diagonal. It would be something like the identity matrix minus the sigma z matrix divided by 2. Okay, so the is a analogy. So corresponding to the spin down state, you have an eigenvalue for the sigma z minus 1. So 1 minus 1 divided by 2, you find out this one here. And the main, the eigenvalue for that state would correspond analogously to spin up, and this is corresponding to the plus eigenstate of the sigma z, which is the zero particle state. But it's just, remember, it's just an analogy. It is not, it has nothing to do with the spin of the particle. It's just analogy between the Pauli matrices and the fermionic operators for a matrix representation of fermionic operators. Okay? So in next lectures, we already introduced the Bosonic and Fermionic algebra, and in next lectures we will discuss a little bit more on how to quantize a field theory. Some more aspects will be needed, but see you next time.